This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write.
Alright everybody, welcome to section 5.2, day 2, exponential functions. And just to give you a little roadmap of where we're headed and what this is all about, in the very opening of the chapter, 5.1, we talked about inverses. The inverse of f would be f of negative 1, f inverse. And then, last notes of section 5.2, day 1, we talked about exponential functions, like f of x equals 2 to the x. Well, today, in 5.22, we're going to talk about what is the inverse of an exponential equation. So we're going to take what we learned at the very beginning, and we're going to apply it to what we just learned and now produce something new. What is the inverse of these kinds of exponential functions? So let's just remind ourselves what we know about exponential functions. We've got, so for example, a very common, simple, compared to others, exponential function would be y equals 2 to the x. Your inputs here are 2, 1, 0, negative 1, negative 2. And then when you put them as exponents, you get these numbers out. Well, when we call these numbers, these input would be exponents. You can see they're written here in the exponents. The 2 itself would be the base. And then these are what we call powers. Like 2 squared is 4, and that's a power of 2. 1/2 is technically a power of 2, even though it's smaller. It's a power of 2 because 2 to the negative 1 is 1/2. So, exponent base power. So, let's talk about what that would be. Here, y equals 2 to the x in an exponential equation, and then we have the inverse. And notice the difference between these two is that we just interchange the x and the y. Here, for exponential equations, the input was an exponent and the output was a power. So, we can flip those. The input would be a power and the output would be an exponent. And if you think about it, it's kind of strange. What kind of function would need to take in a power and produce as an exponent? Anytime you're wondering what is the exponent, then you're going to have to use the inverse exponential equation. Anyway, we've got a domain here from negative infinity to positive infinity. Here, the exponent could be positive or negative, and then the range will always be 0 to infinity, at least in this particular equation. That gets switched. Our domain is no longer all real numbers. Our domain is only going to be the numbers from 0 to infinity, all positive numbers. And then the range will be from negative infinity to positive infinity. It gets switched in the inverse. We've got an intercept of 0, 1. That's because when you put 0 in for x, 2 to the 0 is equal to 1. So that's one of your points, 0, 1. And in fact, if you change the base to be y equals 3 to the x, or 5 to the x, or e to the x, then the y-intercept is still going to be 0, 1, because any base to the 0 is equal to 1. Well, that changes here to an x-intercept. And so you can see, if you plug in 1 for x, the only way you're going to get a power out is if you make sure you have a 0 as an exponent. 1 is equal to 2 to the 0. That's an x-intercept in the inverse and a y-intercept in the original. Then, of course, there's an asymptote. There's a horizontal asymptote, y equals 0. Eventually, these functions, exponential functions, will go down very close to the x-axis at a horizontal line of y equals 0. And so when we take the inverse, that gets flipped. It's now a vertical asymptote at x equals 0. What does that look like graphically? Well, on a table, you can see we're flipping the x and the y. These are all the powers, and these are all the exponents. And if you're making a table and graphing these things, it's going to be a lot easier just to choose the y's. Let's say you had a more complicated, let's say you couldn't copy this table from before, but you actually really had to calculate the x values. It's just a lot easier to calculate, to not guess the x's, but instead to demand, okay, I'm going to say, I want to know what I have y values, -2, -1, 0, 1, 2. I'll plug them into the equation and calculate the x values. It's a lot easier to go in this direction. because that's what we've been doing so far. So if you have to do these, then work the table backwards. If you plot all those points, you'll notice here are the different. Here's the graph right here, the original and then the inverse. So let's look at that inverse. It does have a domain from 0 to infinity. There is a vertical asymptote of x equals 0. There is an x-intercept of 1, 0. There is a range of negative infinity to positive infinity. Let me talk to you a little bit about growth factor. Growth factor, I find, is a really great way to represent a percent increase. Let's say you wanted to increase something by nothing at all. Let's say we had no change. One thing you could do if you wanted to multiply it would be take $100 times 1. $100 times 1 is going to produce $100, and there will be no change. However, compare that to an increase of 1%, you can multiply that by 1.01. $100 times 1.01 will increase it by 1% to up to $101. So you can see that although they both have a 1, this one has a 1.01. The growth factor is slightly larger. How much larger? 1% larger. So $100 times 1.02 would be $102. That's increasing it by 2%. Similarly, you could start with a 1, and then you could decrease that by 1% to get 0.99. Multiplying, you get $99. That's a 1% decrease. And also, you could do the same thing with a 2% decrease. $100 times 0.99. That'll give you $98. Check out how this works if on a word problem. Let's say you wanted to take $50. If you start with $50 shoes on sale for 20% off, that means you want a 20% decrease. You could multiply 50 times 0.80. That's 100% minus the 20% gives you 80%. You're really only paying for the remaining 80%, so you can multiply it by 0.80. This is the growth factor right here, and coming up with this is the tricky part, but once you do, then just multiply and you get your answer. $250 plus 5% sales tax. So you got the $250 and then multiplying it by 1, but not just 1, a little bit more than 1, 5% more than 1, 1.05. That's when you multiply here, you get your answer. Now the great thing about thinking about percent increase in this way is that you can actually stack them on top of each other. You can start with a $75 dinner. You can add a 7% tax by multiplying by 1.07, and then you can also add a 15% tip by multiplying by 1.15. You get it all in one expression, and it's just a lot cleaner. The work is much less messy, and it has a wider application. You can stack 2 or 3 of these on top of each other in the same expression and type them all into the calculator, hit enter once, and then you're done. 3% interest on $1,000 every year for 3 years. Well, then you would start with $1,000 original, and then you'd multiply it by your 1.03 3 times. For every year for 3 years, you're going to increase it by 3%. Now, this is the long way of writing it, but actually there's a shorthand way, $1,000 times 1.03 to the third exponent. If you're going to multiply 3 times in a row, you might as well just use an exponent. It's much simpler to type that into a calculator, and we can actually come up with a formula for something like that. So this is interest compounded annually. The answer, the final amount, if you're going to put in money into a bank, very much like we had right here, 3% interest on $1,000. Now, no one's going to get 3% interest at a bank, but let's say you're investing that money and you're going to get 3% back in the real world. So let's say this is the P, the principal or starting amount, and then you're going to multiply it by this growth factor. Remember, it's 1 plus some percent. And the really tricky thing is that it's usually given in word problems, like I said, above 3%. You have to convert that to a decimal, like we see in the growth factor. You have to change it to 1 plus the decimal. Here, 1 plus I. And then however many years you're going to be multiplying it by, you just put it up there as t, time in years. So check this out. Suppose that $100,000 is invested at 8% interest, compounded annually. Compounded just means you're applying the interest annually. Find a function for the amount of in the account after t years. So remembering to change 8% into its decimal 0.08, we can say that it's going to be this: 100,000 times 1.08. That's the 8%. 1 plus 8% there. And then what we don't know is how many years. That's going to be a function. You give me the years as an input, and then calculate this, and I'll give you the output and how much money you'll have invested. Find the amount of money in the account at 0, 4, 8, and 10 years. So what I've done is I've put it into Desmos, and f of t equals all this. So it's going to look, in order to calculate these numbers, it's going to look over here at t1, and then 0, 4, 8, 10. 0, this is, if there's no interest at all, then, there's no time, then there's no interest. So you have your original amount, and then you have, after you're gaining interest, this is what it would look like. I want you to put all this into Desmos, and I want you to actually calculate how much money you would have in 10 years. Of course, you can graph this, and you can see that we've got a curve right here. This curve is going to be made out of aluminum. Aluminum is your audio check element for today. Aluminum, the 13th element on the periodic table. This aluminum curve is going to be curved upward slightly. You really have to notice, if you're going to get a graph like this, you're really going to have to adjust the scales. You can't just click the zoom out button. You have to be very intentional about making sure the x-axis doesn't expand at all. I'm only looking from 0 to 10, and then we're going from 0 to 200, 300,000. It's not a square zoom at all. It's very rectangular. Anyway, that's how you make those graphs. And then what I'd like you to do is start the assignment 5B2, copy the problem list, and do the first problem. And I'll see you in class.